We were Team 5. This is our breakdown of one of Macau's most daring buildings. For our project, we chose Morpheus Hotel, a four-story tower with no internal columns wrapped in a freeform exoskeletons. Our story begins not with the building, but with the land beneath it. Originally, this entire area was open sea. Through decades of land reclamation, what was once ocean is now one of Asia's most iconic skylines. But how did this strip of land come to exist in the first place? In 1990s, land was reclaimed to connect the island of Taipa and Koloan. The name Kotai was inspired by these two islands. Kotai was reclaimed for additional casinos and hotels. But on this reclaimed land rose something bold, a resort called City of Dreams. City of Dreams opened in 2009, built by Melco Resort. It's a resort with casino, theaters, restaurants, and 4 hotels, including Morpheus. Its brand promise is Dream Beyond. Luxury, arts, and imagination in one place. But this dream needed a centerpiece. In 2012, Melco CEO Lawrence Ho approached one architect, Zaha Hadid. Other Macau hotels copied Vegas or Europe. He wanted something only Macau could claim. City of Dreams needed an architect of dreams. Hadid, the queen of curves, turned fluid form into reality, and so the hotel was named Morpheus. We chose Morpheus because it's not just a beautiful building. It where design asks the impossible and engineering answers. Reclaimed ground, double curved glass, no internal columns. This video unpacks how it was solved. Most buildings hide their bones. This one turned them inside out. The world's first freeform high-rise exoskeleton in Macau. But cutting hole through a tower creates a serious problems. Cut a hole and forces pile up at its edges, stress concentration. And this is Macau, typhoons and earthquakes included. So, the skeleton moved outside. The whole skin becomes structure. Dense where loads are heavy, lighter as it climbs. A web of 2,500 connections. But a skeleton alone is not enough. Where does all that force go? We say no columns, but 3 systems share the work. 2 concrete cores from the spine, columns beside them assist, and the exoskeleton carries the skin. Now, follow a single force, it gathers at a node. A short stop beam reached 600 mm through the skin, and hence the force across horizontally cleanly. The quite genius, every node sits exactly at the slab level. Misaligned, the force would bend the beam and waste itself. Aligned, it travels straight into the slab, the core, and to the ground. But here was the real challenge. Every part was different. Over 1 million unique parts, nearly 25,000 cladding panels. No two exactly alike. Drawing them by hand would take weeks of modeling. And no single beam file could even hold them all. So instead of drawing, they wrote rules. In Rhino and Grasshopper, with the Elephant plugin, the entire facade was generated as data, baked every night in 5 hours. A mesh over the surface, each vertex a node, each edge a member. Panels, sorted, brackets, and fasteners placed automatically. $1 million parts, 350,000 drawings by a team of just 4. But would it actually stand? We tested it in the same model. Using Caramba 3D, the team simulated the structural load path and confirmed the stress at the center stayed within safe limits. A skeleton room on the outside made buildable by code. Structure became its face and computation made it real. Next, I will explain the construction stage. First, 2 massive reinforced concrete cores were erected, each standing 160 meters tall, responsible for bearing the entire vertical load of the building. These twin cores served as the structural backbone of Morpheus. As construction continued, the freeform exoskeleton had to be installed. However, it could not support itself until the full structure was complete. To keep the structure stable while steel nodes were welded on site, massive temporary support towers were erected first. To carry the 4,500 tons of steel until the exoskeleton could stand on its own. These first work towers took over the gravitational load until the exoskeleton reached structural self-sufficiency. The welded nodes were then sequentially integrated into the exoskeleton. Once the core reached a certain height, the exoskeleton and interior floor slab were connected via stub beams. This allowed the enormous load and stretches acting on the exterior to be transferred directly and efficiently into the cores without any bending. The result was a completely column-free interior, achieving the open, unobstructed space the design demanded. Yet another challenge emerged during construction. Because of the exoskeletons, wrapping the building, it was impossible to install the facade panels using cranes and gondolas from the outside as in a typical skyscraper. To solve this, the construction team developed an innovative solution. Large macro panels pre-assembled at the factory were pushed outward from inside the building and installed from the interior, not the exterior. This reversed installation logic made it possible to clad the entire facade safely and precisely. Hong Kong and Macau are frequently hit by heavy rain and typhoons, making waterproofing critical to the building's longevity. In typical buildings, standardized rubber gasket seals the joint and prevent water from seeping in. But Morpheus has 2,500 steel nodes, each one a unique shape. Standard gasket simply cannot fit them all, leaving gaps that leak. To solve this, our team proposed introducing 3D printing. In the actual construction, nodes were grouped into categories, and multiple standardized gasket types were factory produced. We took this one step further. Using the 3D file data for every individual node, we identified the exact size and geometry each gasket required and proposed fabricating them on demand with 3D printing. Through this entire construction process, Morpheus has been reborn as one of Macau's most iconic landmarks.
Now let's turn to wrap the entire building. Each glass facade. Look closely and you'll notice no two panels are alike. Every section curves in two directions at once, what we call double curvature. Can this even be built from the flat glass? Initially, pole bending was considered. It's cost-effective and efficient, but the contractor lacked the experience, and construction quality could not be guaranteed. The answer came from geometry itself. 3 points are ways to find a single plane. So any curved surface, no matter how complex, can be built from flat triangles. And that's the same principle is right there on the building stuff. Each glass panel of Morpheus is a flat triangle. To apply this across thousands of panels, we needed an algorithm. It reads each panel's curvature and assigns the right panel type triangular. Finally, we built this algorithm ourselves in glass software. It sorts every glass panel by curvature. Reconstructing the Morpheus facade, watching its curves resolve into flat triangular panels. Standing in the heart of Macau's Cotai Strip, this is not just a hotel. The Morpheus is the world's first free-form high-rise exoskeleton. Total construction cost was US $1.1 billion. Out of that, the facade alone consumed $1.1 billion. A single package accounting for 12% of the entire project budget. For context, that proportion is highly unusual for any single trade in a construction project. From now on, we examine why this happened and what our team proposes to do about it. The root cause of this cost explosion is curvature. The Morpheus Hotel exoskeleton aluminum cladding covers approximately 57,000 square meters. Of this, 21% of the total is double curved surface. And within the freeform exoskeleton zone specifically, 67% is double curved or twisted. Single curved surfaces that bend in one direction, and double curved surfaces that curve simultaneously in two directions. There are three fundamental surface types in facade engineering. Double curved panels can cost 5 times more than flat panels. The Morpheus exoskeleton contains 2,048 nodes, and every single one with the different surface geometry. This is the fundamental reason facade work consumes 12% of the total project budget. So is this high cost economically justified? To answer this, our team analyzed actual financial data from Macau results. TF Dreams Macau's EBITDA is the follows. The implication is clear. Morpheus and as an iconic architectural landmark is generating a brand premium, driving occupancy demand and attracting visitors to the entire resort complex. Iconic design creates long-term commercial value, and that value is accelerating the recovery of the initial investment. But we asked one more question: could we have preserved the design intent and still reduced the cost? Our team's approach was to apply a 30mm cold bending offset tolerance, algorithmically approximate each node's surface to other simpler, more manufacturable geometry. Step 1. Curvature classification using Gaussian curvature and principal curvature analysis. All 2,048 nodes are automatically sorted into 3 categories: perfectly planar, single curved, and double curved. Step 2. Planarization of single curved surfaces. For single curved nodes, a normal plane is generated as a geometric center of each surface. The curved geometry is then projected onto this plane, converting it into a perfectly flat fabrication ready. Step 3. Cylindrical approximation of double curved surfaces. For double curved nodes, principal curvature analysis identifies the dominant curvature direction. A best fit cylinder is generated and the surface is projected onto it, transforming the double curved geometry into a cold bendable single curved form. Here are the results. All 997 double curved nodes are reduced to 0. Planar nodes increased from 226 to 948. Single curved nodes rise from 825 to 1100. To quantify the cost impact, we applied conservative fabrication cost multiplier. Flat at 1, single curved at 2.5, and double curved at 5. In practice, these ratios can be significantly higher. These figures represent a conservative lower bound based on academic literature. Applying these multipliers, the rated average fabrication cost per node is reduced by approximately 49%, all while keeping visible deviations within 30mm of the original design geometry. Morpheus Hotel is not merely a beautiful building. It is the convergence of digital design and construction technology making the impossible real. Thousands of regular glass panels, 2,500 unique exoskeleton joints. No two pieces alike, yet one parametric algorithm wove this complexity into a single order. What this project taught us is clear. In architecture, impossible is no longer where the story ends. Define the problem, decompose it with algorithms, solve it with the right tools. This process itself has become the new language of modern architecture. The curves Zaha Hadid left behind were not just forms. They were a challenge demanding answers to countless technical questions. And the journey of finding those answers, that is the greatest insight we gained from Morpheus. We will conclude our presentation by showing our references and sources along with a video of a construction process we created. Thank you.